All right, let's start. So, both in organic chemistry and in thermochemistry, the standards talk about intermolecular forces. Yeah. And just as a reminder, when we talk about intermolecular forces, we are talking about the bonds between molecules. So just as a nice little reminder, if we had, for example, a water molecule, I love water because it's such a good example. And we did this last year, so I'm hoping you guys have some prior knowledge on it. So when we are talking about the bonds between, say, for example, the oxygen and the hydrogen, where they're sharing electrons, we call that an, intramolecular bond. So it's intra, think about inner, it's inside the molecule. The other way I like to remember it is that it's traumatic to break it apart. It requires quite a bit of energy. The intermolecular forces are the bonds between my molecule. So that's what that guy is. Think international travel. You're traveling from one molecule to the next. Now, if you guys remember last year in structure and bonding, molecules fall under the category of covalent molecular solids, and that's going to be the kind of key focus in your thermochemistry exam. So if you guys remember last year with the structure and bonding, you had a question on the different types of solids, and there were 4 different types of solids that they talked about. The ionic, the metals, the covalent network, and the covalent molecular were the 4. This year is going to be really focused on the covalent molecular for this question. When we are thinking about covalent molecular, a lot of molecules are organic substances. So that's how this then parallels to organic chemistry, is that since this is a topic all about molecules, organic compounds are generally molecules because they're not very long. So that's where these two things overlap. Now, some things to remember about these intermolecular forces is that it doesn't require a lot of energy to break because they are very weak. So these are very weak bonds. Therefore, require little heat energy to break. Therefore, we see things have a low melting and a low boiling point. And I'm going to abbreviate melting point as MP and then boiling point. You know me with my shorthand. You gentlemen going to write anything down, or are you just going to stare at it? Make sense? Okay, this is stuff from last year. All right. What's new for this year is that they're going to want to have more detail with these intermolecular forces. They're going to want you to go into more specific categories. So this year we're going into more detail. We're going to be more specific. Yeah. So there are 3 that we are talking about. So we're going to break this down. The first one is the strongest of the bonds in comparison. It's not obviously as strong as an ionic bond or a metallic bond or a covalent bond, but in the grand scheme of intermolecular forces, this is a strong force. So the strongest one that we're going to be talking about, and thus requiring the most heat energy to break apart, is going to be your hydrogen bonds. And I think we have talked about this last year as well. The hydrogen bond is an example of a polar bond. But this one is really special because the hydrogen is attached to something very electron negative. Yep. You guys okay with me abbreviating this as electronegative? Yeah. Okay. Yeah, electronegative. I'm just lazy. Don't do that on the exam. But you guys have plenty of time to write on the exam. I don't. All right. So our very electronegative atoms, there are 3 that we are concerned about. That's going to be the nitrogen, the oxygen, or fluorine. If my hydrogen is attached to one of those, it then has the potential to form hydrogen bonds. The reason why is because these atoms are so electron negative, they're going to pull the electrons very, very close to the electronegative element. So it's kind of like quite a big electronegativity. The thing we have to remember is that hydrogen, when we look at it atomically, the nucleus only consists of 1 proton. So when I pull those electrons so far away from the hydrogen, I'm essentially exposing a proton. Backtrack? I heard a what? Which is essentially just a proton. So that's why that one's the strongest of the bonds. We have quite a unbalance when it comes to this polar bond. So that's something to keep in mind when you guys are looking in the thermochemistry lens. You are looking to see, is the molecule that they have provided for my question, is it a hydrogen attached to one of these 3 things? If it's one of these 3 things, then you'd state that hydrogen bonds are possible. In the context of organic chemistry, so I'm just going to write a little note for organic. A little side note. There are a handful of functional groups that do that as well. Remember, it needs to be the hydrogen attached to the electronegative element, not just the electronegative element existing in the molecule. So we can think about potentially OH is one of those that can do a hydrogen bond. We're thinking about the OH in the alcohol and in the carboxylic acid. And we're also going to be thinking about the NH, which we see in the amines and the amides. Outside of that, we don't have to worry about the hydrogen bonding. Questions, concerns, comments? I'll leave it up for a second because I can see you guys are still writing. Alrighty, so that was our first one. I'm just gonna lighten this up because I think it's a bit dark. Okay, The second one that we have, and this is kind of like the middle of the rank when it comes to strength, is going to be, I'm just trying to figure out what color I want, is the permanent dipole. And those doing thermochemistry, we covered this when we talked about polarity. I just didn't give you guys the name for it. So dipole, di means two, poles mean area of different charges. This is just a molecule with a polar bond, basically. The permanent dipole. So we always have an unequal distribution of charge. Unequal distribution. No, I can't spell distribution. And we've talked about polarity for thermochemistry, so it's just in reference to that. All right. The last type of intermolecular force that we're thinking about is the temporary dipole. Now this one here is the weakest of the three. So do keep that in mind, weakest guy. What happens with a temporary dipole is we have, say, for example, a nonpolar molecule, and by random chance, the electrons just congregate together. So you have to remember the electrons are moving around, and randomly they can just congregate and group. So say, for example, I have a nonpolar molecule like chlorine, and we know there's electrons in that electron cloud. A temporary dipole would be, for chance, the electrons kind of congregate around one of the chlorines instead of the other one, making one end slightly negative and the other end slightly positive. So just randomly, the electrons kind of congregate to a section. And what these guys can do is they can also induce other molecules to form a temporary dipole as well. So if this becomes slightly negative, if a chlorine molecule is next to it, it can then also induce it to become positive, and then this one becoming more negative. Are we okay with that as an idea? Some things to keep in mind with these temporary dipoles is that this is more likely to happen the larger the atom is. More likely to occur the larger the atom is. So basically, if we go down the periodic table, bromine's more likely to form a temporary dipole than fluorine at the top because it's a bigger atom. The other thing is if we have more atoms in the molecule, the more likely it's going to do this. So for example, and this can apply both for organic chemistry and thermo, if I have, say, for example, propane versus butane, 1, 2, 3, 4, 5, this guy over here is going to have more temporary dipoles than this one over here. and that's because that one's larger. So if we're thinking about the snowball effect of that, it's going to then require more energy to break all those temporary dipoles and thus have a higher melting and boiling point. Okay so far? Ready for the last note on this? And then thermochemistry is done. Well, this component of the material that applies to thermochemistry. All right, the last thing to keep in mind with these temporary dipoles is the shape of the molecule. The straighter the chain, the easier it is for it to stack. So if I have a straight chain, it will have a higher melting and boiling point because there's more temporary dipoles. I'm just going to add in that note, higher melting point and boiling point. So say, for example, again, if I have that pentane, sorry, not butane. So that's my straight chain. If I have the same molecule, so my structural isomer that is branched, has less temporary dipoles. So for example, if I have something that looks like this, that shouldn't have any hyphens on it. So this, on the other hand, is going to have fewer temporary dipoles. The reason why is because this guy can stack. It can stack nicely and thus form lots and lots of intermolecular forces. Whereas this guy, it's going to have a harder time trying to fit together. So it's like basically these guys form these nice little chains, whereas this would have a hard time as a shape to make those intermolecular forces. It's going to struggle, not going to make as many. I'll give you a second, and then I'll show you guys how this looks on the exam. And this exam question applies to both organic and thermo. Because I can stick this on an organic exam if they're not feeling like nice. Can I move it? Nope. Can I move it now? Can I move it now? Good. Okay. I just want to show you guys what this question looks like. I want NTA exams. And is this level 3? It is level 3. Are these exam papers? Yes, they are. All right. I wanted to show you the 2021 one because I did find a question that kind of parallels both. That was question 3A. Here you go. So this is an example of how they then ask this question on thermochemistry. In theory, they could also ask the same question on organic chemistry because they've chosen organic molecules. So that's why I want to point it out to you guys, just in case. It doesn't come up often on the organic exam, but it might. And so that's why I wanted just to show it to you guys and do this kind of combined lesson. So in this case, they've given you 3 different molecules. And in this instance, they've given you all organic molecules. They've given you the enthalpy value for vaporization. So how much heat energy do I need to put in in order to get this to change from a liquid to a gas. And they've given you these values, and they want you to state the attractive forces, and they want you to then justify with the relative strengths what would be, like, why is their boiling points ranked as they are. So some things to keep in mind is this one you are naming if it has temporary dipoles, permanent dipoles, or hydrogen bonds. Keep in mind that all molecules have temporary dipoles, regardless of what they are. So all three of these, you should be writing temporary dipole. This one, you would write that there are permanent dipoles because of the oxygen here. That's going to cause a permanent pole there. The rest of the organic chain is more or less nonpolar, so thus the temporary dipoles. The propanoic acid and the pentanoic acid both can form hydrogen bonds because we have the OH there. Do keep that in mind. The last thing is comparing these two guys. So in this case, the propanoic acid is a larger molecule. It can form more temporary dipoles, and that's why this one has a slightly higher vaporization energy than this one. Just kind of pointing out what this question looks like so you guys are aware. Cool, and that's it for the thermo lot. Just FYI, I think that's only Klein who's doing just the thermo. So Klein, just so you are aware, there are some SciPad pages that you can do to help. I've put in some extra ones as well on ionic bonding. They may ask it, but it's more likely they're going to focus on the covalent molecular. But just in case, it's worth kind of reviewing the bonding and the melting and boiling points of ionic, metallic, and covalent networks. Or you can work on the collated question. All right, everybody else is organic or both, so you guys are going to be listening up to the second part of the notes. Do you guys want a little bit of a break? Okay, give you guys a little bit of a break.